Hi everybody, I'm Dr. Tim Floyd, and today we're going to talk about operations with functions. Now, this is a skill that you need all the way through algebra. I mean, there is no place you don't need to be able to do this, because what you learn as you learn about functions is simply that functions represent numbers. Well, just like numbers that can be added, subtracted, multiplied, and divided, we can do the same thing with functions. So that's what we'll get into in this lesson. So, some things we need to talk about first. If I can get my slide to move. Okay. Functions represent numerical values. That means we can add and we can subtract, we can multiply and divide them. The same thing we can do with numbers, we can do with functions. Now, it doesn't mean that we come out with a numerical answer. It means that sometimes we come out with a new function. In fact, most of the time you come out with a new function. Now, possibly in a lesson you've already had, one of the issues we will need to discuss as we do this is the domain that we get in our final answer. The domain are the values that we can substitute for x. The domain is the list of all possible numbers. Usually it begins with all real numbers, that fancy R that you write, whichever way I'm writing it in the sky. It always begins as all real numbers, and usually we pull things out when we talk about domain. But we have an answer, and we have to also talk about domain. Now, the second thing I had on the slide is there is one additional operation because they're functions. We put things in for the variables, which means we can do something called the composite of two functions. It will have a symbol for it where add and subtract and multiply and divide have symbols that signal those. Composite also has a symbol which is a small little circle. It's usually written in the middle between the two function names, and it's a small circle. It is not a letter O, and it's not a dot. It's just a little open circle. If you're doing this on your computer, it's in the symbols of the word processing program. So with that in mind, let us then also begin with adding and subtracting. Now, I have made a list of functions. Now, in a lesson possibly before this lesson, you may have talked about what makes a function. A function is a rule so that you have x values that do not repeat. So in other words, if you have an x value that's connected to two different y values, it's not a function. So right now we're talking about function arithmetic. We could do some arithmetic with relations, but we're going to do it with functions today. Now, what I've written on the slide is I've just named 4 functions that we're going to use in the upcoming problems. Now, you might want to take a moment and write these down so that you can see them as I go through the next slides. Either that or you want to rewind back to see these. But these are just 4 functions that I've made up. They could be any 4 functions. I just wanted to start with some simple ones just to get the idea of arithmetic with functions going. Now, when you add and subtract, the main idea is remembering to combine like terms. If you remember, the like terms have the same variables, and each variable has the same exponent. When you then combine like terms, you combine the coefficients. If you have a distribution to do, make sure that you properly distribute negatives. This will come up when we subtract. And coefficients can be any type of number. They can be whole numbers, they can be fractions, they could be decimals, they could be radicals. But when we combine those, then you just have to know how to add that type of number. Now, if it's fractions, and you will have a lot of fractions, it would be good for you to learn how to do fractions. Either remember how to do them the old-fashioned way, or learn how to put them in your calculator and get the correct answer. So you do want to keep a calculator handy as you're doing these problems. If you know how to add fractions without a problem, then wonderful. That's a skill not a lot of people have anymore. But most people grab the calculator and do their arithmetic on that. All right, so let's launch into some examples of this. All right, let's look at the first problem. Now if you'll notice, I have f of x plus g of x, and we go back to the list of functions that I just had on the previous slide. So we get those two functions, and now we're going to add them. Now remember, we talked with adding, we're going to be combining like terms. Now when I write function operation problems, I tend to put parentheses like a variable where I'm filling in for the variable. We had function f was 5x minus 4, and function g is 2x squared minus 5x plus 7. Now, if I'm using parentheses, what I have to do is think about if anything would distribute that's going to change anything. Well, of course, there's a positive 1 in front of, understood to be in front of this, so it doesn't change anything. So we simply have 5x minus 4. Now, in front of the second, we have an understood plus 1. Now, it's not as critical here. I know this is an extra step for most of you, but it will be very critical when we're subtracting in a few moments. So if we distribute positive 1, we simply get 2x squared minus 5x plus 7. At this point, making sure all of our signs are correct, we now combine like terms. Starting with the highest term, which is the 2x squared, there is no other term like 2x squared, so we simply write it first. Now we have 5x minus 5x. Well, that's going to be 0. Now we could write 0x, but normally in books when you write final answers, you don't write 0x as the answer. So we're just going to write that term. And then we have minus 4 plus 7. So we get 2x squared plus 3. And that is our new function, f plus g. Notice, we don't get a numeric answer, we get a new function. Now, one of the things, as I mentioned earlier, we need to be concerned about is domain. There are two areas that we are concerned about domain. One is if the variable is in the denominator. Well, in this case, we have no variable in the denominator. Our domain always starts out as all real numbers. And if we have a variable in the denominator, we have to exclude values. Well, in this case, there is nothing to exclude, so our domain is all real numbers. Now, some of your teachers will have you write this, or let you write this, as this fancy R, I call it, the double back R. Another way teachers might have you write the domain would be in set builder notation, the set of all x such that x is an element of the real numbers. Again, it's up to your teacher as to what form they want you to write the domain. Now, in many problems, they simply want the answer, and if that's the case, then that would be the answer that you would write. Read your directions carefully. If it says write the domain with your answer, then go back and write the domain. The next problem is we're going to subtract two functions. Now here's where you have to really be careful, especially about the second function. Okay? Again, we have function f, if you look back at that list, is 5x minus 4. And then we're going to subtract function g, which again is 2x squared minus 5x plus 7. Now, there's nothing that changes in the 5x minus 4, so we simply leave it as 5x minus 4, not 5. Okay? Now, on the second, what we have is an understood -1 in front of this expression. So we need to distribute properly that -1. Make sure you distribute it completely through. So we have minus 2x squared plus 5x minus 7. Okay? Now, we combine like terms. We have negative. Make sure you bring the negative with it. If we put these in order, it begins with negative 2x squared. 5x plus 5x would be plus 10x. And then minus 4 minus 7 gives us minus 11. And again, this is our new function, f minus g. We could give it its own name if we wanted to. We've used f, d, g, and h. We could call this k or any letter that we want. But normally, they just, in problem sets where you're doing these, you would just simply write f minus g equals this. Now, our domain in this case, again, is all real numbers, and you can write that, again, understand how your instructor wants you to put that to make it look correct. Now, the next problem, I just simply want to show you that the order of subtraction is important. We have g minus h. So, if you go to the list of functions, again, we're using g, which I've used a couple of times already, which you might maybe have memorized by now, is that I've used it a couple of times. 2x squared minus 5x plus 7. But now we're subtracting a new one of the other functions now, h, which was 5x squared minus 7x plus 2. Here again, we're subtracting, so you've got to be very careful that you change all the signs in this second function. So we have 2x squared minus 5x plus 7. We have minus 5x plus, 5x squared plus 7x minus 2. Notice they were positive, negative, positive. Now we're negative, positive, negative. All three signs. And the biggest mistake people make, usually they'll forget to do the last one, the sign right. That will cause you to get the wrong answer, which means you miss the problem and miss whatever you're doing with it. Okay? Now we combine our like terms. 2x squared minus 5x squared gives us minus 3x squared. Negative 5x plus 7x gives us plus 2x. And plus 7 minus 2 gives us plus 5, if we write this in order. And this is g minus h. Here again, we have no domain restrictions here. So our domain for this function, again, is all real numbers. Now, what I want to show you then is if we turn this around, we get a different answer. Let's say that we make this h minus g. Now, if we do that, you have to be very careful because it's now the h function first, which was 5x squared minus 7x plus 2. And this time we're subtracting g, which was 2x squared minus 5x plus 7. Here again, we have to think about that as being a negative 1, and you have to distribute it completely. So we end up with 5x squared minus 7x plus 2 minus 2x squared plus 5x minus 7. Now this answer is going to look a lot like the previous problem, but the signs are going to be different. We get 3x squared minus 2x minus 5. But that's still a different answer. And our domain is going to be all real numbers again. So when you're subtracting and adding, if you come to me for a minute, when you're adding and subtracting, be very careful then that you distribute the negative correctly and that you combine your like terms correctly. Keep in mind some of the expressions can have fractions, so you have to work with fractions. Now, let's talk about multiplying functions. Now, in this case, we have to bring in an old friend, at least it's an old friend of mine, I hope it's an old friend of yours, FOIL. we have to make sure that we multiply correctly. So in this case, if we go back to the list of functions, we have function f times d, which, and notice it could be written f of x times d of x, f times d, or simply write the variables together side by side. Now, the function f, here again, I want to put parentheses in place of, it's like filling in for a variable. So we have 5x minus 4, and we have 3x plus 7. Now we're multiplying. If you saw this problem back in your basic algebra, this is a typical FOIL situation. You have to multiply the first terms together, the outside terms, the inside terms, and the last terms together to make sure you get this completely correct. 5x times 3x is 15x squared. Excuse me. 5x times 7 is plus 35x. Negative 4 times positive 3 is minus 12x. Negative 4 times 7 is minus 28. Now to finish simplifying this, usually the middle two terms will combine. And so we get 15x squared plus 23x. 35 minus 12 would be 23 minus 28. So that is our new function f times d. Now again, ask ourselves about the domain, we have no variables in the denominator and we have no square root. So in this case, the domain, if you're asked for the domain, is all real numbers. Okay, now suppose we do f times g. This is still a FOIL situation, but it's just a little bit longer. Again, f is 5x minus 4. And now g, if we go back down the list, is 2x squared minus 5x plus 7. Now what we have is, it's like multiplying a 2-digit number times a 3-digit number. When we do the FOIL, you do the first term times all three of those numbers, and the second term times all three again. So you're going to multiply 6 things together. So we have 5x times 2x squared, which would be 10x to the third. 5x times negative 5x is negative 25x squared. And 5x times 7 is plus 35x. Now, negative 4 times 2x squared is negative 8x squared. To help, and it also saves space, is I'm going to line that up under, since I'm going to be adding like terms anyway, I'm going to line it up under the 25x squared. We got minus 4 times minus 5x, which is plus 20x. And then minus 4 times 7, which gives us minus 28. So our function, new function f times g, is 10x to the third minus 33x squared plus 55x minus 28. And again, we have no variables in the denominator, no square root situations. So our domain, the values we can put in for x in this is all real numbers. This could be an interesting function to put in your calculator and graph. The numbers are big, so you would have to alter the window to be able to see it. But when you go to cubic functions, you start getting some very interesting things with your graph. And that graphing is another lesson down the line. So one other thing about multiplying that I want to make sure you understand is we don't always have to be multiplying two functions. We could be multiplying a number times a function. So let me make up a problem here that I forgot to include in my slide. Let's say we have 2 times g. That's a multiplication. All we're doing is multiplying 2 times the function g, which would be 2x squared minus 5x plus 7. So if you have 2 times g, this is simply a distribution then of, make sure you do that, all the multiplications correctly, so we get 4x squared minus 10x plus 14. So if you have, and by the way, if you get into future algebra, this is called scalar multiplication because we're multiplying by a constant value. Now, we have multiplied, we have added and subtracted. Now we want to talk about division. Functions can possibly be divided using, actually they can be divided using true long division process or synthetic division. But in your book, for most of these problems, you're simply going to leave the answer written as a fraction. You're just going to, like with all fractions, you're just going to make sure it's reduced to lowest terms. Now there is an additional concern. Here we will have some situations where the denominator cannot equal 0, so you must have things excluded from the domain. So let's look at our first, now here I'm going to use some new functions. So this f of x is not the same f of x I used in the other set of problems. You'll use f of x a lot. It's like using the letter x as a variable. So here we have f of x and g of x, and now I want to do f, and the slash mark means divided by. Now of course we could have f of x divided by g of x. Most of the textbooks won't use the old-fashioned division symbol, but they might. Now the other way this could be written is it could be written just formally as a fraction. That is still a division problem. Okay, now in this case we have f divided by g. So if f of x is x minus 4 and g of x is x squared minus 3x minus 4. That is our answer. We just now need to see if it will reduce. In order to reduce, you factor the numerator if it will factor, and you factor the denominator if it will factor. Now, in this case, x minus 4, and I'm going to put parentheses around this because many folks would be very tempted to cancel x's. You cannot cancel x's if they're added or subtracted to something else. Now, x squared minus 3x minus 4, if you go off the page and do some factoring with this, you end up with x minus 4 times x plus 1. That is how x squared minus 3x minus 4 factors. Now here we have to ask ourselves, we have variables in the denominator. So now we have to say to ourselves, well, we can't divide by 0. So x minus 4 cannot equal 0. So x cannot equal positive 4. Also, x plus 1 cannot equal 0. So x cannot equal negative 1. So when we do our domain, we have to exclude those values. And by the way, now, when we reduce this, if you remember when you reduce expressions, if they're identical, we can cancel them. Well, x minus 4 is identical to x minus 4, so we can cancel those. And since there is nothing else in the numerator, there is a 1 left behind. So this becomes 1 over x plus 1, and that is your final answer. That is f divided by g. But when we talk about the domain, some teachers will let you just write it this way. All real numbers except 4 and negative 1. Now you might say, why do I have to exclude the 4? It got canceled. One of the spirit of the domain here with these problems is that if x minus 4 was one of the parts of the problem originally, it has to be excluded even though it's no longer in the final answer. So you don't do your domain from the final answer. You do it from the initial, when you set up the division or when you set up the problem with the two functions or however many functions you have. It's very important that you do your domain at that point before you reduce it. Otherwise, you will leave something out of the domain in the final answer and something will be wrong. It might cost you some points on the test or have a wrong answer if you're doing something later on in your life with engineering or science. It's very important that that be left out. So in this problem, we have to leave out the 4, even though that term canceled. Now, if we want to write this, let me just take a brief moment and I'll show you about interval notation. If we put our exclusions in order on the number line and we put an open circle there, we can basically have any real number except for those two values. Now, all I'm doing is, in school you may have been taught to shade the line or to write the bar above it. But basically we have the entire number line except for these two numbers. Well, what we have then, if you're writing this in interval notation, is we have 3 intervals. So if you're writing this in interval notation, we'd go from negative infinity to -1 with a parenthesis on the -1. Then we go from -1 to 4 with parenthesis in the -1 and the 4. And then we go from 4 to positive infinity. And we connect these with a U for union or unite, whichever way you want to think about it. So this would be the way you would learn to write the domain in interval notation. It's a little complicated. Hopefully in your text, or maybe there will be a lesson at some point that will review interval notation. If that's the case, then you do probably want to go back and watch it if this is something new to you. Okay, now let's go to the next problem. All right, and I just have created different functions here. So I've got h of x is 3x squared minus 21x, and k of x is 21x to the 5th. So I want to do h divided by k. Again, now this is a different h than I had back on the slide when I was adding and subtracting. You have to do whatever the function's defined as at that problem. So we have 3x squared minus 21x divided by 21x to the 5th. Now, I know some of you are very tempted to start like 3 go into 21 or the 21 into the 21, x cancel. That is not how we can reduce this. You reduce by factoring. Okay, it's very important. You use factoring to reduce. Now, again, before I go on, I have an x in the denominator, and it's simply an x. X cannot equal to 0, so I have to leave that out of my domain. Now, the numerator, 3 and 21, I can factor out a 3. I have x squared and x, I can factor out an x. So the top factors with a common factor of 3x, leaving me x minus 7. The denominator is a single term, 21x to the 5th. Now, these are the pieces now. I don't have an x minus 7 in the bottom, but these are the pieces now that I can reduce. And when we do that, 3 will go into 21, leaving 7. X to the 1st, x to the 5th will leave me with x to the 4th. So I have x minus 7 over 7x to the 4th. And that is h divided by k. And with or without, it wouldn't be wrong if you left parentheses around the x minus 7. Normally the problems don't. Now here again, the domain is all real numbers except 0. If we write this in interval notation, we have a hole at 0, but we have everything else around it. So we have negative infinity to 0, united with 0 to positive infinity, if we write it in interval notation. Okay? Now, The last function is a new function. Composite is a new thing. We can't do it with numbers because numbers themselves don't have variables. But since we have expressions with variables, we can substitute things in for the variable. Well, why not substitute entire functions? And that's what this process is. The symbol for composite is a small circle. So we do get these funny looking words. In fact, we say circle. So a lot of teachers will say F circle G. Now I know that looks like fog. You do have to be careful if you're making up function names. You can get some strange little words here. But we wouldn't call that technically fog. We would call it F circle G, or the composite of F into G. Now the order of this is very important. The composite of G into F. F circle G means that we're going to take G and we're going to put it inside of F. Now I'm going to refer to the first function as the dominant function. Let me spell dominant correctly. Okay, the first function is called the dominant function. This is the function that we will use to create the look of our final answer. The second function goes in for the variable that's in the first function. So that's the sequence that we're plugging this in. So F circle G means that we've taken G of x and we put it in where this would normally be F of x. We have put in G of x in its place. That's what composite means. Now, let's look at this first problem. We have an f of x is x squared minus 2x plus 1, and g of x is 2x minus 3. Now, if we do f circle g, what you do is you look at that and you say, okay, f is the dominant function. So I take and write the structure. Let me change my ink colors here for a second. So I take the function f and I write that function, and everywhere there's an x, I put an empty set of parentheses. Okay? I like to do that with variables. When I have a variable, I put an empty set of parentheses anyway and put what I'm putting in. Well, in this case, what we're going to put in for the variable is this function g of x. We're going to put in 2x minus 3 for the x squared, and we're going to put in 2x minus 3 in for the 2x. Now look at that for a minute. That is the beginning of our answer. We're not done yet, but that's the first step that you've got to get correct. Now, at this point, many people get this right, okay? But what you've got to be careful of now is now we want to simplify this down to a simple expression, which means do FOIL and add or subtract like terms. Okay, so now what we're doing is, this is the actual substitution. We are now going to simplify. And I know you always hate it when math teachers say simplify because we're not necessarily making it simple. So 2x minus 3 squared. Now let me remind you that that's 2x minus 3 times 2x minus 3. We have to do the FOIL. So we get 4x squared minus 6x plus 9. So we have 4x squared minus 12x plus 9. So the first part of this is 4x squared minus 12x plus 9. Now in the second one, we are distributing negative 2, so make sure you get the signs right. Negative 2 times 2x is negative 4x. Negative 2 times negative 3 is positive 6. And then we have, don't forget the function f had a plus 1 that didn't have a variable with it. So we don't put anything in there, we just have to write it. Now, to simplify this, we have 4x squared. We have minus 12x minus 4x would be minus 16x. We have plus 9 plus 6 is plus 15, plus 1 would be plus 16. And that is the composite F circle G, or FOG. Now, with domains, when we're doing composites, we have to be very careful. First of all, G is the one we're substituting. G has no restrictions. So that's the first thing you do when you're doing domain. You look at the one you're substituting, the second one, not the dominant one, but the second one. We're substituting that function had no restrictions. Then we look along the way in this problem here, and if at any point we have x in the denominator or square root of x, then we have restrictions. Well, that didn't happen. So here our domain, if you need to write, is all real numbers. Now frankly, when you see the problem sets for this, you will not have to write the domain on all of these answers. Most of them just want the answer, but you will have to. It may be that your teacher will expect you to write the domain on every problem you do. So you'll have to keep that in mind. All right? Now let's look at the next problem. Okay, I have a function f of x and a function g of x. And again, g and f get used a lot. So remember, don't pull one that was on a previous problem that was a g or an f. Make sure you're using the one for the current problem. Now, we want to do g circle f. That means g is the dominant function. Now, that means when I write g circle f, I write the structure of G first. Since it's first, it's the dominant one. It's going to determine the structure of the answer. Now, not many teachers maybe refer to, when you're doing composite, that the first function is the dominant function. But I like to use that term because you have to use it to write the structure. And then F is the one getting substituted everywhere there's an empty set of parentheses. So what we have then is 2 times x squared minus 2x plus 1 minus 3. Now be very careful, make sure, the real southern, you can tell, any of you that may watch this in the future, you may be from the north. I'm originally from Chicago. I didn't used to talk this way, but I've been in the South so long I just have to talk like a southerner, you know. So you have to watch out as you do this to make sure that you do the distribution correctly. So we get 2x squared minus 4x plus 2. That's distributing the 2 completely. But now don't forget the minus 3. It's kind of out there, doesn't have a change, but we have to include it. Now we're ready to write our final answer, 2x squared minus 4x minus 1. And that is G circle F. Now notice, if this was F circle G, F would be the dominant function, and it would look very different than this. Now, let's talk about domain. F was the one that got substituted. There are no domain restrictions for F. There were no point in the process where we created a variable in the denominator or a square root. So therefore, our domain is all real numbers. Just to remind you that if you wrote it out in words, all real numbers. Okay? Now, you could also, if you wrote this in interval notation, write this as negative infinity, positive infinity. Now, that is the composite of 2 functions. Now, suppose we have 3 functions. So we have h, let me slide this down a little bit. We have h circle G circle F. Okay? What we're going to do is we'll do this in stages. G circle F, that's the composite where G is dominant. And then that answer goes into H. So what I would do is do G circle F first. So what we have for that is G is dominant, so it's x squared. G is the structure of the answer for this piece. And by the way, we go from right to left. I know that's weird, but you do work right to left. So we do G circle F first. Now, F is x minus 3. So here again, we substitute the F function into the G function. Now, we don't have any domain restrictions here. So we get G circle F. Now, make sure that you do x minus 3 times x minus 3. You're going to have a middle term here. You get x squared minus 6x plus 9. If you come to me for a minute, my experience with people doing composite functions is they'll get the initial substitution done correctly, but then miss the problem because they don't FOIL or don't add like terms correctly. So this is going to be very frustrating for some of you to get these answers correct. But I guarantee you it's progressive. You have to eliminate mistakes to get to the final right answer. So be very patient with yourself. Don't put pressure on yourself because you don't get the right answer the first time. Go back, make sure you made the correct substitution, and then make sure you did the correct simplifying. And you will be on your way to getting correct answers, especially on one like this that's very long. So if we go back to the problem now, G circle F is x squared minus 6x plus 9. Now, what we're doing then is H is the final dominant, and we are substituting what we got for G circle F into H. So H circle G circle F means we substitute, we have H as the dominant in this case, so we have 3x minus 2. And inside of the x that was in H, we plug in this function. So we have x squared minus 6x plus 9. So we get 3x squared minus 18x plus 27. Make sure you do that distribution correctly. Now don't forget the minus 2. So we get 3x squared minus 18x plus 25. And that is H circle G circle F. Composite is an entirely different thing from adding, subtracting, and multiplying and dividing. It's something new. You've never done it before. So it will take practice. The other thing will be is getting domains right as you work on some of these. Depending on what kind of function you're substituting, you will possibly have domain restrictions. Your textbook should have examples where you have domain restrictions. Possibly there will be a video on this by itself at some point. So look through your video package and see if you have a video for the domain of composite functions. If not, use your textbook or your reference book to double check that. Now, as at this point you have gotten the basics for adding, subtracting, multiplying, and dividing functions and the composite. Consult your textbook. Many of your problems when you do these will be because you don't simplify correctly or you don't FOIL correctly. Go back to videos or go online or go to your reference material and review FOILing, adding and subtracting like terms, rules with exponents. And with domain, you have to review domain restrictions. And when you pull all these, this is one of the first areas where we begin to pull a bunch of pieces together to do big problems. And that's what the future of your future in algebra is. You start doing problems that take you a page or 2 pages of paper, oh my God, for you to get the right answer, okay? So take your time, be careful. You will get a little frustrated initially, but the more you do these until you get them right, the better things will be. I thank you for watching this video, and I would like to say good night, Miss Calabash, wherever you are.